Hello. In this video, we're going to look at proof by contradiction. Now, while none of the specific problems and proofs from this video are going to be on a test or on an exam, the methods that we're going to use here are very applicable to the course we're learning and to future math courses. Because what we're going to look at is how you would prove something using a contradiction. And, for example, we could prove that there is no largest number. Now, this is probably a fact that you know. You know that numbers continue on and on. There's 1, 100, 1,000, a million, a billion, infinity. Numbers go on and on. There, of course, is no largest number. You might even argue that this doesn't need a proof. But if you were to prove it, how would you do it? And it would seem kind of difficult to try to prove that there was no largest number. It almost seems like the thing you couldn't prove. And so what you do is you start with the opposite. So you suppose whatever the opposite of the statement would be. In this case, the opposite of there is no largest number would be that, of course, there is a largest number. Maybe the largest number is, let's say, L. Well, this is the beginning of our proof. We suppose the opposite of what we're trying to prove. So we suppose that there is a largest number, L. And then what you do is you try to produce a contradiction, something absurd. Somehow this supposition, this assumption must lead to just a ridiculous claim, which means that what you suppose must be wrong and the alternative must be the truth. So if we assume there's a largest number L, what we do is we then consider the number L plus 1. This number L plus 1, we add 1 to L, is clearly a larger number than L. A larger number than L. Okay, so what just happened? Well, we suppose there was a largest number. You could think of this as your friend said, I know the largest number, a million. And you said, well, look at the number a million plus 1. This is clearly a larger number. And you could play this game with a billion plus 1, a trillion plus 1. Anytime you think you have the largest number, you simply add 1 to it, and you have a number that is larger. So what this means is that to suppose there was a largest number, L, is impossible, because you get another larger number, L plus 1. So L cannot have been the largest number, but you said it was. And so this is a contradiction. It's impossible. Which means, therefore, instead of saying that there is a largest number, we can say the opposite. There is not a largest number, or there is no largest number. And that completes our proof. Let's take a look at a bit more of an involved proof, a bit more of a challenging proof. We might ask the question, how many prime numbers are there? Now, you hopefully remember the primes, numbers like 2, 3, 5, 7, not 9 because 3 goes into 9, but 11 and 13 and so on. And you might ask the question, do they stop? Is there a biggest prime number, or do they go on forever? That's really our two options. Either there's a finite number of primes or there's an infinite number. And let's suppose there are a finite number. So we are going to suppose there are a finite number of primes. Well, what we do is we list them all. So we're going to list all primes. Because if there are a finite number of them, then that means you could count them. There's a list. So we're going to list them as P1, P2, all the way to Pn. Pn being that last prime. Well, now what we're going to do is we're going to make a new number. We're going to consider the number you get when you take P1 and you times P2 and you times all the way up to Pn. Now if we look at this number, we're actually going to notice that it's divisible by every one of the primes. So clearly this big number is not prime, and we'll say that. This number is divisible by all the primes, so it is not prime. This number is not a prime number. Alright, but what if we add 1 to it? What if we take this number and add the number 1? So we'll consider P1 times P2 times Pn plus 1. Well, if you were to try to divide this number by P1, you'd have a bit of a remainder. If you divided it by P2, P3, Pn, because P1, P2, P3, Pn all divide into that first number, when you add 1, well, you've got remainder 1 in each one of these divisions. So this number here is not divisible by any of the primes. This number is not divisible by any of the primes. Thus, it must be prime. A number is prime if the only number that divides into it is 1 in itself, and since none of the primes divide in, this new number must be a prime. So this number right here, we have found a prime. Now, here's the catch. If you notice, this number is very big because it's all of the prime numbers added together, or multiplied together, I should say, and then we've added 1 to it. So this number is clearly larger than any of the primes in our list. However, this number is clearly larger than any of the primes in our list. So this prime is not in our list of primes. So wait a minute. This number is huge. It's clearly larger than any of the primes in our list, which means that this number is a prime number that's not in our list of prime numbers. But that doesn't make any sense. We suppose there were a finite number of primes, and we listed them all right here. This is the list of all prime numbers. But we just found a prime number that was not on the list. How could you find a prime number that's not on the list of prime numbers? If this list was all the prime numbers, this prime would be there, but it's not. And that doesn't make any sense. That's a contradiction. So, we have to say that. This is a contradiction. And so, with our contradiction, we must have assumed the wrong thing. And so we had supposed there was a finite number of primes. That led to a contradiction. So therefore, there must be an infinite number of primes. There must be an infinite number of primes. It's a challenging concept. This proof is actually a few thousand years old. It comes to us from ancient Greece. They discovered that there's an infinite number of primes, and they proved it using this method. It's strange, because you suppose there are a finite number of primes, and then you showed that that's impossible, which means the only other option is an infinite number of primes. And Sherlock Holmes has a nice quote that describes the situation we're in. So Sherlock Holmes, in one of his novels, says, "When you have eliminated the impossible, whatever remains, however improbable, must be the truth." And so that's what we do with proof by contradiction. We eliminate something as impossible because it leads to a contradiction. And so whatever remains, whatever the opposite is, no matter how improbable, it must be the truth because it's the only option you have left. And so you might have thought, well, the primes, it seems like we must run out of primes at some point. It seems very improbable that there would be an infinite number of primes, but a finite number of primes is impossible. And so even though it might seem unlikely that the primes go on forever, it must be the truth. Now we're going to look at two problems here, and I really encourage you to try these on your own. They're very interesting problems that involve the mean value theorem as your hint, and proof by contradiction. So I encourage you to pause the video and really try these ones. They're interesting applications of this proof by contradiction method and of the mean value theorem. So assuming you gave these a go, let's try the first one here. Does there exist a function fx such that f of 0 equals -1, f of 2 equals 4, and f prime of x is less than or equal to 2 for all x? What we're going to do is we're going to suppose that this function exists. So suppose such a function exists. Well, because the derivative is less than or equal to 2, then we know the function is differentiable. And if the function is differentiable, it's continuous. And if it's differentiable and continuous, by the mean value theorem, we can use that mean value theorem on the function. So by the mean value theorem, we'd have the following. F of 2 minus f of 0 over 2 minus 0 would be equal to f prime of c for some c in the interval 0 to 2. Well, let's see what we get here if we evaluate that left-hand side. 4 minus -1 over 2. So 4 plus 1 over 2. So 5 over 2. So 2.5. So 2.5 should be equal to f prime of c. Wait a minute. Isn't f prime of c, that's a derivative. Well, we know the derivative is always less than or equal to 2. So we could say, but f prime of c, whatever the value is, has to be less than or equal to 2. So therefore, the number 2.5 must be less than or equal to 2. Does that make sense? Is the number 2.5 less than or equal to 2? No, of course not. This is a contradiction. This is a contradiction. Therefore, no such function exists. It's impossible for a function that meets these criteria to exist, because if it did exist, well, there would be 2.5 being less than or equal to 2, which is impossible. The number 2.5 is clearly greater than 2. So this is impossible. So here's another problem. I encourage you to pause the video and give this one a try. As a hint, you need to use, of course, the mean value theorem, but also the intermediate value theorem. So I'm assuming you gave it a try. Let's see how we can do this one. How many roots does the function have? Well, it's a degree 3, so we know at most it has 3 roots. Let's see if we can find one root. Well, factoring it looks a little tricky. You could try factoring it, but I'm going to plug in f of 0, which will give me -1. And I'm going to plug in f of 1, which will give me 2 plus 3 plus 6 minus 1, which is 10. Notice this is negative, and this is positive. Well, we know that if the function goes from negative to positive, what that means is it was down here below the x-axis and then over here above the x-axis, and so at some point it crossed the x-axis. So the intermediate value theorem tells us there has to be a root. So we can say, so by the intermediate value theorem, or IVT for short, fx has a root between 0 and 1. Thus, fx has at least one root. It's obvious the function has at least one root because we found one between 0 and 1. Now, it's a degree 3, so it could have 2 roots, or it could have 3 roots. We've established that it definitely has 1. So let's go to the next step. But you could try the intermediate value theorem, and you could try a bunch more numbers. But what you're going to find is everything to the left of 0 is just going to give you negatives, and everything to the right of 1 is just going to give you positives. So it's not really going to work to get that flip of a sign. So instead of using the intermediate value theorem, I'm going to show you how we can use the mean value theorem. We're going to now suppose that fx has 2 roots. We're going to see what happens with this assumption. If it has 2 roots, we could say f of a equals 0 and f of b equals 0, because that's what it means to have a root. It's a number. When you plug it in, you get 0. Clearly, we have a polynomial which is continuous and differentiable, so let's go ahead and say, by the mean value theorem, well, what do we have? F of b minus f of a over b minus a should equal f prime of c, where c is in the interval a to b. Okay, well, let's plug in the values we have here. F of a is 0 and f of b is 0, so you're going to have 0 minus 0, 0 minus 0 over b minus a. So 0 over b minus a, 0 divided by anything is, of course, 0. And so therefore, f prime of c is equal to 0. All right, so we've been able to show that the derivative must be equal to 0 somewhere. Well, let's actually calculate the derivative. Looking at that polynomial, we would get 2 times 3, so 6x squared plus 6x plus 6 equals 0. We should be able to factor this and find a value so that it equals 0. That's what we demonstrated here. But if you try to factor that, 2 numbers that multiply, there's a 6 and a 6, so then we've got to add to 6 in the middle. It's looking a little tricky. I'm going to use the discriminant. So let's use the discriminant. We would get the following. So we have the discriminant. We would get 6 squared minus 4 times 6 times 6. So that would be 36 minus 6 times 6 and then times 4, so 144. Ooh, that's a negative number. Well, if we have a negative discriminant, that means, therefore, f prime of x does not factor. Which, of course, means f prime x does not equal 0. Wait a minute. If f prime x doesn't equal 0, but f prime c equals 0, we could even underneath this say if f prime c is 0, well, that means the derivative should be 0 somewhere. But now the derivative is never equal to 0. We could even say this more specifically. And f prime of c cannot equal 0. If the derivative is never 0, that means the derivative at a certain point c can never be 0. But we also know that the derivative at the point c must be 0. So we have the derivative being 0 and the derivative not being 0 at the point c. Can a number be both equal to 0 and not equal to 0? Of course not. Of course not. This is a contradiction. Therefore, f of x has exactly one root. And we'll pull it up on Desmos here just to confirm. So if you look here, it's not a very twisty and noodly degree 3. It's very quick. It's just sort of, again, we can maybe zoom in a little bit here. It comes through the axis at only one point, between 0 and 1. Everything else to the left here goes on down. It flattens out a little bit here. And again, to the right here, it just continues on and up and up and up. So this cubic has only one root. And what's so interesting to me is that you can prove that it has only one root without having to graph it. We simply use the intermediate value theorem, the mean value theorem, some proof by contradiction, and we're able to say so much about the function without actually having to graph it. So hopefully you enjoyed this video and enjoyed some proofs by contradiction. Until next time, thanks for watching.